Right, I'm trying something new with my new device, but it's I've made it seem like it's too close now. But anyway, so this is page 4 of the notes. I'm going to just do this one with you just to help you. I have worked it out already so that we don't have to waste time with me going through trying to do the calculations. Okay, so with the calculator. So what we're looking at is a boy drives his 3 kilogram remote control car. So if we actually, I'm going to ignore the slope here. I'm actually going to draw it as if it was a free body diagram, so that we get used to using the free body diagrams. Okay, so we've got the free body diagram, and it says there a 3 kg remote control moving up the slope, 4 meters long, which is an incline of 25. Okay, so we're moving up the slope, so there must be a force going up to the horizontal. The car's motor exerts an average force of 40 newtons. So this would be the motor, which is 40 newtons, okay, because it's making it go up the slope. The car experiences a frictional force of 15, so that means that is friction of 15 newtons, okay. It moves up the slope. Calculate the net work done. Okay, so let's take up as positive because it is moving up, so that makes sense. We have another force acting on this always and forever, and that is Fg parallel, which is equal to Fg sine, what's the angle? 25. Okay, what else do we need to know? And we know that the x is equal to 4 meters. Right, so we've got everything that we need. So let's take a look. To work out the net work. So remember I said to you there are 2 different ways. You can work out the work for each and every one of those forces. So you would work out 3 works for each force and then add them. Or you can work out the resultant force and then work out the work. I'm going to do it that way because it will help you to get the resultant force, which is pretty much what we normally need for Newton's laws. So, okay, so let's look at it. Let's just get our Fg, which is equal to 3 times 9,8, which is 29,4 newtons. Fg parallel is then, remember, Fg sine 25. So that's that downwards, always down the slope. Okay, and notice, remember, you must draw your free body diagram like that. But if you give the FF and the FG parallel and the F motor, just write on the side what each one means. So we've got 29,4 sine 25, and we land up with 12,42 newtons. Okay, so that is our FGW, parallel. So we've got that force, and now we've got the other force. So we know that the resultant force is equal to the frictional force plus the Fg parallel plus the force of the motor. Okay, we add them all together and then we get our resultant. Right, so I have chosen up as positive. Friction is acting down the slope, so friction would have to be a minus 15 plus a minus 12,42 and plus 40. 40 is a positive, so I can keep it there like that. And this works out to 12,58 newtons up the slope. Okay, so that is our resultant force. So when we're working with the net work, we know that it will be the resultant force times the displacement. Now, we can use cos theta here because it will be cos 0, because our resultant force is in the same direction as the motion. So we could use 0, but that's just going to give us 1. So you don't have to if you know it already. Okay, and and then that's going to be 12,58 times 4 meters, and we land up with 50,32 joules, and that's the answer that's on the page. Okay, you don't have to write up the slope. If you do need to interpret something, you can, it's energy given to the remote control. Okay, work done by the motor on the car, giving the car energy. Right. I have included a think tank 5.1, number 3, 4, and 5. So I've made it so that this is in the new textbook. Let's just go to the second page. Now, this is the work energy theorem. So this is kind of also what, I can't remember what his name was, the video that I let you watch. This is what he was looking at as well. So the work energy theorem, I just want to get it, I've got my STAGS document open. I just want to get the phrasing of the work energy theorem for you properly. Mechanical energy, define work. Okay, the work energy theorem. It just says the work done by the net force, so that would be the net work, on an object is equal to the change in kinetic energy of the object. That is the work energy theorem. So this equation is the work energy theorem. And it literally says the work done by a net force, and that is what net work is, on an object is equal to the change in kinetic energy of the object. Okay, so remember here, we know that this would be then resultant force. You've got to remember that it's the resultant force with the net, or you can call it the F net if you prefer. They're the same thing. Okay, cos theta, and we know that this is then a half m. Now be careful. It says change of kinetic energy, so we're going to use final minus initial. You can use final kinetic energy minus initial kinetic energy. That's fine, you can do that, but that just means that you've got a change in velocity. So that's your final velocity minus your initial velocity in the brackets squared. Don't forget your square. Sorry, it's a little small here. Remember that plus network means energy added. I don't know what I'm doing. And this means energy lost. Okay, sorry, I don't know if you could see that. Okay, so there we have our resultant force, what resultant force is equal to, and what kinetic energy is equal to. Now, very often they give you the question and they either ask you, like here, they say, state the work energy theorem, then you know you're going to use it, or they actually say, use the work energy theorem. Okay, so generally, but who knows what they're going to be doing nowadays. All right, so let's take a look at this. So we have a box of mass 300 kilograms. Okay, so I'm going to draw my free body diagram again over here. Okay, slides along the surface of a rough, so we know that it's going to be friction. Okay, rough friction, inclined at an angle of 20 to the horizontal. It passes X when moving to, we've got this is our initial velocity and this is our final velocity. Slides further 12 meters and enters the water at 5 meters. Right, sorry about that. I had too much storage on my phone and it stopped recording. Okay, so we're back live. Well, not live, recorded. Okay, so we're talking about that we have a final velocity. Okay, so it's sliding down. So, and there's no, as far as we can tell, there's no force acting on it to make it go down other than my FG parallel. Okay, so, but we do know that because it says it's a rough surface, we do have friction. We can take down as positive now because it's just going down. So it's easier to take the direction is positive that it's moving in. All right, so we are going to use the work energy theorem because it actually asked you to state it. So the best way to do this is to, if you're not sure what to do next, just write it down, okay? Is there something that twigged our memory here? Absolutely, that change in kinetic energy. What do we know about this? We know that the resultant force times the distance is equal to that. So if we get what our work net is, we can work out our resultant friction. And that's the question. It says calculate the magnitude of the net force acting on the box as it is sliding down. So I'm going to work out my W net. You can substitute the work net formula in and then work it out in one go, but I'm just going to show you this way. All right, so we know it's going to be a half m VF minus VI all squared. Okay, so that is 300 kilograms, 5 minus 2 squared. And luckily I did this already on the calculator, so we don't have to waste time. And we know that it's 1,350 joules. Okay, so now what I know about that is that work net is equal to the resultant force times x. Now again, I can put cos 0 over here. You don't have to, because we know that the resultant force is positive. Yeah, that's right. The resultant force must be positive because it's moving down. And the direction is down, so that's fine. Okay, so, and also because we are not losing any energy, so the friction's not taking, so that was positive, so we know that it's adding to it. Okay, and it is because it's getting faster. It went from 2 to 5. All right, so we have that. We are looking for our resultant force. We have 12 meters, and so our resultant force is equal to 112.5 newtons, and that's going to be down the slope. Okay, I would suggest you say down the slope instead of just down. Okay, so we also know that F res is equal to the sum of the forces, and we've only got 2 forces, and I'm going to then add them. So FG parallel plus FF. Now, you're going to say, why don't I subtract it? I don't have to. It will work out as a negative. Okay, so it's actually better for you to add all your forces and substitute if you have them as negatives, or let it work out to a negative. Okay, so this is our resultant force. Our FG parallel, that is going to be FG sine 20. Okay, and if I work out my FG, that's 300 times 9,8 plus FF. This works out to be 1005,54. Okay, obviously you can show you're working out for that. All right, and so my friction works out to minus 89. Remember, you're going to subtract here when you take that over 04 newtons, 893,04 newtons, and obviously you would say equals to 893,04 newtons up the slope. Right, and there it is. So please, would you do the other activity in this? I'll give you some time to do it in class as well. Okay, thank you. I'll speak to you now.